Our universe, for instance, is the Milky Way galaxy, and the closest galaxy to us is the Andromeda Galaxy. We think there are around 100 billion galaxies in the observable universe. The Andromeda Galaxy has been instrumental in reshaping how we might interpret the universe and our place inside it. For example, while our galaxy is the Milky Way, the closest one to us is Andromeda. We gauge there are around 100 billion galaxies in the observable universe. This disclosure gave undeniable proof that the universe and the idea of creation don't revolve around Earth. It broke the notion that the Milky Way was the sole galaxy in existence, suggesting we are simply a minuscule piece of the vast universe. Our understanding of Andromeda has developed over the course of the past century, principally through observations made on Earth. However, with cutting-edge instruments like the James Webb Space Telescope, JWST, now available, our viewpoint has radically changed. Shockingly, recent information from the JWST has challenged our past ideas about the Andromeda Galaxy, presenting a new and enormous riddle to tackle. The JWST has received extraordinary signals from our neighboring galaxy, leaving mainstream researchers flabbergasted. Join us as we explore how the JWST has provided startling insights into the Andromeda Galaxy. The view of the Milky Way has evolved significantly throughout humanity's history, shaped by our growing understanding of the universe. In the past, when our technological capabilities were limited, the Milky Way appeared as a hazy band of light across the night sky, inspiring various interpretations and folklores. It was often seen as a magical and central component in the cosmological beliefs of different cultures. During the 1920s, Edwin Hubble, an American astronomer, made a groundbreaking revelation using the 100-inch Hooker telescope at Mount Wilson Observatory. Through observations and analysis, Hubble showed that the faint clouds beyond the Milky Way were, in fact, distinct galaxies, each containing billions of stars. One of the nearest of these galaxies was the Andromeda Galaxy, also known as M31. Andromeda has a rich history of observations going back hundreds of years. One of the earliest known records of this celestial object can be traced back to the 10th century, when the Persian astronomer Abdul al-Sufi described it as a small cloud in star charts from that period. The significance of these observations lies in the fact that al-Sufi was able to identify this distant celestial entity without the aid of adjustable instruments, relying entirely on his keen vision and observations. Later, in 1612, a more detailed description of the Andromeda Galaxy based on telescopic observations was provided by Simon Marius. His work laid the groundwork for future astronomers to study this massive celestial structure. In 1764, the prestigious French astronomer Charles Messier classified the Andromeda system as M31 in his famous Messier catalogue, erroneously crediting its discovery to Simon Marius, ignorant of al-Sufi's prior work. For nearly 100 years after this, astronomers were collectively trying to learn more about this mysterious system, each adding to the previous discoveries. Before that, Galileo Galilei, an Italian astronomer, fundamentally changed how we might interpret the Milky Way in the mid-17th century. Using his newly developed telescope, he made pivotal observations that challenged the prevailing Aristotelian cosmology. He found that the Milky Way was not just a diffuse band of light but rather a vast collection of individual stars, planets, and other celestial objects. Through his observations, he demonstrated that the Milky Way was not at the center of the universe, as previously believed, but rather a vast array of stars dispersed throughout space. In 1750, English astronomer Thomas Wright proposed a new hypothesis in his work, A New Hypothesis or New Theory of the Universe. According to Wright's hypothesis, the Milky Way was not an irregular distribution of stars in space but rather a flat layer of stars. He also suggested that a part of this vast structure was our own solar system. While Wright's theory was a step in the right direction in understanding the structure of the Milky Way, it was still limited by the observational technology available at the time. They still believed that the Milky Way was all there was to it, and considering the constraints, this was not surprising. A significant leap in understanding the nature of the Andromeda Galaxy occurred in 1864, when English astronomer William Huggins made a remarkable observation. He studied the spectrum of Andromeda and noticed that it was different from that of a typical nebula. This paved the way for the galaxy to be recognized for what it truly is. While it's large, The Andromeda Galaxy has a mass estimated to be somewhere between 1 and 2 trillion times that of our Sun, a massive celestial structure residing relatively close to us in the vastness of space. All the research conducted up to this point suggests that Andromeda is around 10 billion years old, making it very old in cosmic terms. Its age indicates a long and complex history of formation and evolution. One of the captivating aspects of Andromeda's origin is the theory that it formed through the merging of several smaller protogalaxies. This suggests that, over billions of years, smaller entities gradually came together under the force of gravity to form the magnificent Andromeda Galaxy we see today. Such cosmic mergers are common events in the universe, shaping the formation and structure of galaxies. For a long time, astronomers thought Andromeda was significantly larger than our own Milky Way galaxy. From an observational standpoint, such a mistake could easily be made because we are in our own galaxy, and seeing Andromeda from Earth makes things look so large that one would easily imagine that nothing could come close to its size. However, that is not the case. Galaxies are enormous systems, and their mass is intricately linked to the distribution and movements of stars, gas, dust, and dark matter within them. Pinpointing these attributes precisely is a demanding task that requires complex observational techniques and meticulous analysis. This kind of information requires modern instruments, which is why the truth is becoming apparent now. Recent research has led to a reassessment of these beliefs. New discoveries have prompted scientists to somewhat reduce their estimate of Andromeda's mass while simultaneously increasing the mass attributed to our Milky Way. Thus, the current understanding is that the two massive galaxies are much closer in mass than previously thought. The Andromeda Galaxy's actual dimensions, however, are well established. It is known to extend farther than our own Milky Way, with a grand diameter of around 220,000 light-years. Andromeda surpasses the Milky Way's estimated width of around 100,000 to 175,000 light-years, making it a truly massive celestial entity spanning a vast region of space. This revised perspective also highlights the complexities and challenges of accurately measuring the mass of galaxies. At the core of the Andromeda Galaxy, the extremely massive black hole exerts a tremendously strong gravitational pull on surrounding stars. As these stars orbit around the black hole, they follow curved paths, similar to planets circling the Sun in our solar system. At certain points in their elliptical orbits, stars come closest to the black hole, known as the periastron. At the periastron, the gravitational forces are at their strongest, causing the stars to move at their highest speeds. This is when the stars bunch up and become more densely packed in space around the black hole. As they cluster, the stars emit energy as radiation, including visible light and other forms of electromagnetic radiation. The increased concentration of stars and the release of radiation create the brighter point of concentration that astronomers observe in the galaxy's core. The core of the Andromeda Galaxy contains an active galactic nucleus, AGN. An AGN is a highly energetic region at the center of a galaxy characterized by intense emissions across various frequencies, from radio waves to X-rays. AGNs are powered by the presence of a very massive black hole at the galaxy's core. These supermassive black holes are extremely dense regions in space where a tremendous amount of mass is concentrated within a tiny volume. When astronomers observe active galactic nuclei using advanced telescopes like the Hubble Space Telescope, they notice a fascinating phenomenon. One of the most intriguing features of the Andromeda Galaxy is its AGN, which seems to have 2 points of concentration. There are 2 distinct regions where light and other forms of radiation are emitted more strongly than in the surrounding areas. The brighter concentration is the second point of focus, which is slightly off from the actual galactic center. Within this region lies the supermassive black hole, which has been estimated to be between 11 to 23 million times the mass of our Sun. Supermassive black holes are believed to be common in the centers of galaxies, including our own Milky Way, and play a crucial role in the formation and dynamics of galaxies. When matter such as gas and stars gets too close to a supermassive black hole, it forms an accretion disk around it. This disk of swirling material heats up and emits intense radiation across various frequencies, which is why the AGN is highly luminous. When astronomers observe the active galactic nucleus of the Andromeda Galaxy, they notice a brighter point of concentration near the central supermassive black hole. This feature results from the unique gravitational interactions between the black hole and the stars in its vicinity. The Andromeda Galaxy also has another truly interesting feature: a wealth of globular clusters. These globular clusters are dense groups of stars that orbit around the galaxy's center, similar to satellites circling a planet. Andromeda is estimated to harbor around 460 of these dense and ancient clusters, each containing thousands to millions of stars that formed around the same time. The large number of globular clusters in Andromeda provides valuable insights into its astronomical history and interactions. The study of the Andromeda Galaxy has uncovered many fascinating details beyond its size and structure. One of the most intriguing aspects of Andromeda is its interaction with the Milky Way. The two galaxies are on a collision course and are expected to merge in about 4.5 billion years. This future cosmic event, known as the Milkomeda or Andromeda-Milky Way merger, will likely lead to the formation of a new galaxy. The interaction between the two galaxies will reshape both, causing dramatic changes in their structures and star populations. The impending collision has been a subject of significant study as it will influence the future of our galaxy and solar system. As Andromeda and the Milky Way approach each other, their mutual gravitational pull will trigger a series of cosmic events. Stars in both galaxies will be disturbed by these interactions, but due to the vast distances between individual stars, direct collisions between them are unlikely. However, the gravitational forces will cause significant changes in the orbits of stars and might trigger new star formation as gas clouds collide and compress. One of the methods used to study these interactions is through simulations and models. Astronomers use sophisticated computer simulations to predict how galaxies interact and evolve during such mergers. These models help scientists understand the potential outcomes of the collision, including the formation of new star clusters and the reorganization of stellar orbits. Additionally, these simulations offer insights into how the structure of the Milky Way and Andromeda might change over time, providing a glimpse into the future of our galactic neighborhood. Another interesting feature of Andromeda is its population of satellite galaxies. These smaller galaxies orbit around Andromeda, much like how the Milky Way has its own system of satellite galaxies. The study of Andromeda's satellites provides valuable information about the galaxy's formation and evolution. Observations have revealed that Andromeda has a number of irregular and dwarf galaxies in its vicinity, which are likely remnants of smaller galaxies that were accreted by Andromeda over time. These satellite galaxies offer clues about the processes that shaped Andromeda and contribute to our understanding of galaxy formation in general. One notable satellite galaxy of Andromeda is M32, a compact elliptical galaxy that orbits very close to the main galaxy. M32 has been of particular interest to astronomers because of its unique characteristics and its interaction with Andromeda. Studies have shown that M32 may have been significantly affected by its close proximity to Andromeda, leading to its compact and dense structure. Observing such interactions helps scientists understand how gravitational forces can shape the evolution of smaller galaxies and influence their properties. In addition to studying the structure and dynamics of Andromeda, astronomers also investigate the chemical composition of its stars and interstellar medium. By analyzing the light from Andromeda's stars, researchers can determine their chemical makeup, which provides insights into the galaxy's history of star formation and stellar evolution. The chemical elements found in stars reveal information about the processes that occurred in the galaxy over billions of years, including the formation of heavy elements through stellar nucleosynthesis. Another area of research focuses on the dark matter associated with Andromeda. Dark matter is an invisible substance that does not emit or interact with light, but exerts a gravitational influence on visible matter. The presence of dark matter in galaxies is inferred from its gravitational effects on stars and gas. Studies of Andromeda's rotation curve, which plots the velocity of stars and gas as a function of distance from the galaxy's center, have revealed that dark matter plays a significant role in shaping the galaxy's mass distribution. Understanding the distribution of dark matter in Andromeda is crucial for unraveling the mysteries of galaxy formation and the overall structure of the universe. The study of Andromeda's star clusters also provides valuable insights into its past. These star clusters, which are groups of stars that form together and are bound by gravity, can be classified into two main types: Open clusters and globular clusters. Open clusters are younger and contain fewer stars, while globular clusters are older and more densely packed. The globular clusters in Andromeda offer a glimpse into the early stages of the galaxy's formation and its subsequent evolution. By examining the properties of these clusters, astronomers can learn about the conditions under which Andromeda's stars formed and how the galaxy's structure has changed over time. The Andromeda Galaxy also exhibits a range of stellar phenomena, including supernovae and variable stars. Supernovae are explosive events that occur when massive stars reach the end of their lives, and their remnants can provide valuable information about the processes occurring in a galaxy. Variable stars, on the other hand, are stars whose brightness changes over time due to intrinsic or extrinsic factors. Studying these stars in Andromeda helps astronomers understand the diverse stellar populations within the galaxy and their contributions to its overall structure and evolution. In recent years, advancements in observational technology have allowed astronomers to study Andromeda in greater detail. Space telescopes like the Hubble Space Telescope and the James Webb Space Telescope have provided high-resolution images and spectra of the galaxy, revealing new information about its structure and components. These observations have led to discoveries such as the presence of new star clusters, the detection of faint stellar streams, and a better understanding of the galaxy's overall morphology. The continued study of the Andromeda Galaxy remains a key area of research in astrophysics. As our observational tools and techniques advance, we gain deeper insights into the nature of this neighboring galaxy and its role in the broader context of the universe. The knowledge gained from studying Andromeda not only enhances our understanding of our cosmic neighborhood, but also contributes to the fundamental principles of galaxy formation and evolution. By exploring these various aspects of the Andromeda Galaxy, astronomers continue to unravel the mysteries of our universe, shedding light on the processes that shape galaxies and their interactions. The ongoing research into Andromeda and its myriad features ensures that we will keep learning and discovering new facets of this remarkable cosmic neighbor for years to come.